Hello, students, and a very warm welcome. Today we're going to revise one of the most important chapters in all of chemistry, the structure of the atom. Understanding this chapter is absolutely key because it builds the foundation for everything else you will learn. So let's get ready for your exams and make these concepts crystal clear.
Here's a quick look at what we'll cover in our revision today. We will start with what's inside the atom, then look at how our ideas about the atom changed over time with different models. We'll understand Bohr's model, learn how to arrange electrons, define what gives an atom its identity, and finally, I'll give you a simple guide for your exam preparation.
All right, let's begin right at the beginning. The first, most basic question is, what is an atom actually made of? For a long time, scientists had one idea, but as you'll see, the real answer was much more exciting. So John Dalton, a famous scientist, proposed that atoms were the smallest possible things, that you couldn't divide them any further. But was he right? Well, it turns out, no. The discovery of even smaller particles inside the atom, what we call subatomic particles, completely changed our understanding. Now this table is super important for your exam, so let's go through it carefully. There are three main subatomic particles. First, the electron, discovered by J.J. Thomson. Its symbol is E-, and it has a negative charge of -1. Its mass is so small that we consider it negligible, and it's found orbiting outside the nucleus. Second, we have the proton, P+, discovered by E. Goldstein. It has a positive charge of +1, and its mass is considered 1 unit. And third is the neutron, N, discovered by James Chadwick. It has no charge, it's neutral, and its mass is also about 1 unit. Now look at the location. Both protons and neutrons are found packed together in the center of the atom, which we call the nucleus. Okay, so once scientists knew about these three particles, the next big mystery was, how are they arranged inside an atom? This leads us to a fascinating story of discovery, where each scientist improved upon the ideas of the one before them.
The very first person to propose a model was J.J. Thomson, the same person who discovered the electron. In 1904, he tried to explain how the positive and negative charges he found could exist together in a single atom.
So Thomson came up with what we call the plum pudding model. A better way for us to imagine it is like a watermelon. He said the whole red part of the watermelon is a sphere of positive charge, and the black seeds are the negatively charged electrons stuck inside it. The most important point of his model was that the total positive charge was equal to the total negative charge, which explained why an atom as a whole is electrically neutral. It was a good start, but it wasn't the full picture.
And this is where the story gets really interesting. A new experiment, called the gold foil experiment, was performed by another scientist, Ernest Rutherford. And the results of this experiment were so unexpected that Thomson's watermelon model just could not explain them. So what did Rutherford do? He took very fast-moving, positively charged particles, called alpha particles, and fired them at a very thin sheet of gold foil. Here's what he saw. 1, most of the particles just passed straight through the foil. 2, a few of them were deflected by small angles. But 3, and this was the complete shocker, about 1 in every 12,000 particles bounced straight back as if it had hit something solid. Rutherford himself was amazed. He described his surprise with this famous quote. He said it was as unbelievable as firing a big cannonball at a piece of tissue paper and having it come back and hit you. This could only mean one thing. There must be something very small, very dense, and positively charged at the center of the atom. Based on these shocking results, Rutherford gave us a whole new model of the atom. He concluded that, 1, since most particles pass through, the atom must be mostly empty space. 2, there is a very small, dense, and positively charged center, which he named the nucleus. And 3, the electrons must be revolving around this nucleus in circular paths, just like planets revolve around the sun. But, Rutherford's model had a major problem, a really big one. According to physics, any charged particle moving in a circle should lose energy and eventually spiral into the center. So his model suggested that atoms should be unstable and collapse. But we know that's not true. Atoms are very stable. This was a huge question that his model could not answer. And this is a very common exam question, by the way. So, to solve this big problem of the unstable atom, our next scientist, Niels Bohr, came up with a brilliant solution. His ideas gave us the model of the atom that we still use a lot today. Bohr proposed a very simple but powerful idea. He said that electrons are not allowed to revolve just anywhere. They can only exist in certain special, fixed orbits, which he called discrete orbits or energy levels. And here's the most important part. As long as an electron is in one of these special orbits, it does not lose any energy. And just like that, with this one simple rule, he solved the problem of the unstable atom.
We call these special orbits shells. They are named starting from the one closest to the nucleus. We can label them with letters, K, L, M, N, and so on. Or we can use numbers, n equals 1, 2, 3, 4, and so on. The K shell, which is n equals 1, is the one closest to the nucleus, and it has the lowest amount of energy. As we move further away from the nucleus, the energy of the shells keeps increasing. So, now that we have a stable atom with these energy shells, the next practical question is, how do we fill them up with electrons? This is very important, especially for solving numerical questions in your exam. There's a very simple formula to figure out the maximum number of electrons a shell can hold. It's given by 2n squared, where n is the shell number. Let's calculate it. For the first shell, K, where n is 1, it's 2 times 1 squared. That's 2 electrons. For the second shell, L, where n is 2, it's 2 times 2 squared, which is 8 electrons. For the third shell, M, where n is 3, it's 2 times 3 squared, which gives us 18 electrons. Simple, right?
Now let's practice this. Let's take sodium, which has 11 electrons. The first shell, K, can take a maximum of 2 electrons. So we put 2 there. Now we have 9 left. The next shell, L, can take a maximum of 8. So we fill that up. That leaves us with just 1 more electron, which goes into the M shell. So the configuration for sodium is 281. Let's try chlorine with 17 electrons. 2 go in the K shell, 8 go in the L shell, that's 10. We have 7 left, so they go in the M shell. The configuration is 287. Just remember 2 rules. You have to fill the shells in a step-by-step manner, and the outermost shell cannot have more than 8 electrons.
Knowing the electronic configuration helps us find something called valency, which is just the combining capacity of an atom. The rule is simple. If the number of electrons in the outermost shell, the valence electrons, is 1, 2, 3, or 4, then the valency is just that number. For example, magnesium is 282. The outermost shell has 2 electrons, so its valency is 2. But if the valence electrons are 5, 6, or 7, then the valency is 8 minus that number. For example, oxygen is 26. It has 6 valence electrons, so its valency is 8 minus 6, which is also 2.
Okay, we're almost there. Now that we understand the whole structure, we can finally define what makes an atom of carbon different from an atom of oxygen. It all comes down to 2 very important numbers. The first and most important number is the atomic number, which we write as Z. This is simply the number of protons in the nucleus. This number is the identity card of the element. For example, any atom in the universe with 6 protons is and will always be a carbon atom. The second number is the mass number, written as A. This is the total number of protons and neutrons together. Let's look at this example for nitrogen. The number at the bottom, the subscript 7, is the atomic number. This tells us it has 7 protons and therefore 7 electrons. The number at the top, the superscript 14, is the mass number. To find the number of neutrons, you just subtract the atomic number from the mass number. So 14 minus 7 gives us 7 neutrons in nitrogen.
Now, students often get confused between these two terms, so let's make it very clear. Isotopes are atoms of the same element. That means they have the same atomic number Z, but they have different mass numbers A because they have a different number of neutrons. Isobars are the opposite. They are atoms of different elements, so they have different atomic numbers, but they happen to have the same mass number. A good example of isotopes is chlorine, which exists as chlorine-35 and chlorine-37. This is the reason why the atomic mass of chlorine is not a whole number. It's 35.5, which is an average.
We have covered so much today, right from the tiny particles inside an atom to the rules for filling electrons. So, to finish up, let's just quickly summarize the most important things you need to remember for your exam. Here are my final tips for you. First, please practice drawing and labeling the diagrams for the 3 atomic models. It really helps you remember them. Second, make sure you have memorized all the key definitions we discussed, like atomic number, mass number, isotopes, isobars, and valency. Third, practice the numericals, especially calculating protons, neutrons, electrons, and writing electronic configurations. And finally, on the day of the exam, just stay calm and read every question very carefully before you start writing. You have revised the entire chapter now, and you are well prepared. You have a solid understanding of the structure of the atom. So please, stay calm and be confident. All the very best for your exams.